Hey everybody, welcome to the Bite-Sized Statistics video series. My name is Sean Rose and you are watching Module -1, which is going to be an overview of this video series. I apologize for the weird numbering. I already filmed Module 0, which is where we're going to do setup, so I refuse to change the numbering or refilm that video. So this is Module -1, overview. So what is this series? This series is a statistics crash course that is geared towards radiologists, physicists, scientists, grad students, whoever's really got the patience to listen to it, and ideally someone who's gotten stuck in the situation of doing statistics for a research project, but has never really had any formal statistics training, because this is a situation I've been stuck in a number of times. And one of my main goals with this video series is to provide a lot of examples of code of doing things like t-tests, ANOVAs, chi-squareds, logistic regression, linear regression, just general GLMs, whatever. I just want to, personally, I know from my own learning, it's really useful when you have examples of code in R or Python or whatever, to just see how people do these things in practice. And one of the main goals of this video series is providing people with a lot of those examples so that they can get their feet wet and get a feel for how these things can be done. In terms of who I am and why I'm teaching or giving this video series at all, my name's Sean Rose. I'm a diagnostic imaging physics fellow at the University of Wisconsin, and a lot of my experience with these kind of statistics comes from being in situations where we've done some sort of a study in the context of radiology, and someone had to do a statistical analysis, do hypothesis testing, get p-values, measure an effect size, whatever. And basically we have a team of people and none of us are statisticians, so someone has to go and pick it up. And in a number of situations I've been in before, I've been the one that took the time to go through and figure some of this stuff out. So that's my background, and that's why I decided to make this video series, is to sort of help other people out in the future who hopefully don't have to recreate some of the effort that I took in figuring some of this stuff out initially. So, of course, that means I'm not actually a formally trained statistician, so I'm sorry about that. I've taught myself a lot of this stuff. You can consider me sort of a self-taught pseudo quote-unquote statistician. But I promise, I will be open and upfront about stuff that I don't feel confident in. So especially when we get towards the end of this video series and are talking about more fancy stuff, like if we go into linear mixed effects models or something, that's something I've never had to use in my own personal research. And although I will take a shot at going through and learning it myself and explaining it, I will never claim to know anything that I don't have a solid feel for. And I will point you towards what I feel are good resources to understanding these topics. So why am I actually making these videos? Well, I personally am really terrible at memorizing just like tables of names. And if you go to a lot of the journals, at least in the radiology community or in the medical physics community, what I'm familiar with, a lot of times for their guidance on what sort of statistics you should be doing, they give you these really big tables that are like, here are the statistical tests you should do, and here's when you should do them. And I actually really, like, I don't mean to criticize, those are actually really useful tables when you're running some experimental analyses, especially if you're not familiar with the stuff. You're like, oh, well, I have a categorical outcome, I have a couple of continuous confounders, oh, I should apparently be doing logistic regression. Okay, great. But that being said, I'm terrible at memorizing that kind of stuff, and I really wanted to have like a big picture overview of where all this stuff comes from. And I also do want to point you to, even though I'm sort of criticizing that approach, I do want to point you towards this paper in radiographics that actually presents one of these tables, and I think does a really nice job of breaking down how all of these different hypothesis tests can fit together. But actually, just going back to the table from that radiographics paper, so this is, now that I've kind of had to go through a lot of this stuff myself, sort of how I visualize all these things. And I think I get the impression from reading stats books and such, this is how statisticians tend to view a lot of these things. So there's really kind of three different groups of hypothesis tests that people do. You have the hypothesis tests that are geared at continuous outcomes, the ones that are dealing with categorical outcomes, or you'll also hear the verbiage contingency tables a lot. That's where that pops up. And then you have the non-parametric tests. Those are the things like Kruskal-Wallis, Wilcoxon-Rank sum, things that you might have heard of on that front. And the nice thing about these groupings is that in some sense, all of the hypothesis testing you do within each grouping is really related to all of the other hypothesis tests within that grouping. So for instance, for the continuous outcome variables, a lot of times we're using things like t-tests or ANOVAs, or really all of those things are just specific cases of linear regression followed by an f-test, and actually even things like, if you've heard of ANCOVA and multifactorial ANOVA, those all mathematically are actually equivalent to a linear regression followed by an f-test. So you can almost view that entire category as just special cases of linear regression. And of course, there's some caveats to that. Things like MANOVA, if you've heard of that, is not a special case of the usually presented linear regression. And there's Hotelling's t-test, and there's getting fancier with generalized linear models and such. But we'll get into that. The point is you can simplify a lot of the picture of this stuff by looking at these groupings. And linear regression honestly covers a ton of use cases in research. Also, you can do the same sort of thing with the other categories. So for instance, with categorical outcome variables, you have things like the z-test, you have things like the binomial test, which is kind of the same thing as the z-test, but you can do it like with exact confidence intervals and such. You have the chi-square test of independence, you might have the chi-square test of goodness of fit, and these things can actually all be viewed as special cases of doing tests on contingency tables, and that can actually all be viewed as special cases of doing comparison tests after logistic regression if you really want to dive into it deep enough. So again, if you group all these things together, they kind of all just fit in the same category. And then parametric tests are a whole different ballgame, so I'm not going to go into those too much, but those actually are relatively related as well. In terms of the entire course organization, or it's not really a course, but the video series organization, this is what I'm planning on. No promises that I'm going to stick to it, but I'm going to start out with a setup video on the left here, and that's I'm going to do a lot of this stuff using things called Jupyter notebooks. So if you're not familiar with that, that's essentially just a way of putting code in a format where it's cellular. So you have code blocks and you have output, and it's all in one big document that you can send to people. And I think that's a really nice way to share code and share examples of these kinds of analyses. So I'm going to stick with that. Most of the coding is going to be in the R language, just because that's a language that to me is just so nice for statistics. It was developed by statisticians, essentially for statisticians. And I really love it for doing these kind of things. If you are more familiar with Excel or other programming language like Python, Python has the stats models package, which can mimic a lot of the things I'm going to be doing in R. You can do a lot of these things also in Excel. It's a little bit more painful to do it in Excel, but I'm also not one of those people that's going to sit here and tell you like Excel is the be-all or the end of the world, don't use Excel. That's not true. You can do a lot of statistics in Excel if you're familiar with it enough. I personally never got familiar enough with Excel to do these kind of things that efficiently. So I'm going to stick to R and Jupyter notebooks, and I'm going to walk you guys through all of the examples I do and provide the code so you can do it. And in the setup video, I'm going to show you the whole route to getting set up using the Conda, what's called the Conda package manager, to install an R environment and then get set up with Jupyter notebooks. And I'm even going to go into some of the details about specific like extensions I use for Jupyter notebooks, so that you can hopefully replicate exactly what I'm doing on my screen if you want to play around with these Jupyter notebooks yourself. The series is going to be split up into 3 separate routes addressing those categories I talked about in the last slide. So we're going to have the continuous outcomes route. That's going to be route 1. I'm presumably going to film all of that one first, so if you're kind of waiting, I apologize for that. Route 2 is going to cover categorical outcomes, and Route 3 is going to cover non-parametric tests. I called them alternatives here. They're not. There are cases where you almost have to do a non-parametric test. These routes, I'm hoping to film them in such a way that they're essentially separate from each other, i.e. you don't need to have seen Route 1 to go through Route 3, but the modules within each route are going to build on each other. So there's going to be a couple videos, like 3 or so videos in the t-tests module, and then the ANOVAs module is going to assume that you saw the t-tests module. So just my philosophy with this video series, every video is going to provide examples with a Jupyter notebook, except for the, I'm going to start out every module with like a theory video that just gives like an overarching big picture of what that module's about. But other than that, all of the example videos are going to give examples with Jupyter notebooks and R code where you can actually run some examples for yourself. The very first video in the series is going to show you how to get set up with Jupyter notebooks in R in case you've never done that before, and hopefully you can replicate my exact environment. I'm going to try to keep these things pretty efficient. I like to ramble, as you can probably see already just from this video, but I'm going to really try hard to keep all these videos under about 30 minutes, hopefully even faster than that if I can. Regarding mathematics, because I know that scares off a lot of people when they're diving into statistics, particularly if they didn't take a lot of classes in undergrad and such, I'm not going to take the approach of trying to explain things that I personally feel need mathematics to be explained correctly, because I think that hides the bigger picture when I think the bigger picture makes all of these things easier to understand. So I mean, this video series is really geared towards radiologists, physicists, scientists, and these are all, you guys are all pretty freaking smart. You've had to take a good number of math courses. I'm not going to dive into proofs and going into like Cochrane's theorem and showing all of these crazy complicated things. I'm just going to state a lot of theorems without proof and use them in the results. So I'm going to say things like, oh, if you have n IID normal random variables and you construct this thing we call a t-statistic, that thing has a t-distribution with n minus 1 degrees of freedom. And that I'm just going to state that theorem and tell you what it means without proof, because I want you to know that that theorem is what underlies all of the theory we use in constructing t-tests. So, those kind of theorems I really want to present because I think they tie the bigger picture together. But I'm not going to go into a bunch of details and get into the weeds of how to prove those things. Regarding the example data sets I use, when possible, I'm going to use data from real research projects that I personally have done. With a couple of these tests, like the t-test, for example, or even starting off with like the z-test or even some simple chi-squareds, I'm not going to have real data to use for that, and when that is the case, I'm going to use simulated data. The reason for that is primarily because a lot of times, at least in the projects I've been involved with, you're dealing with a lot of confounders. And usually when you're dealing with a lot of confounders, you have to jump all the way to regression methods. So linear regression, logistic regression, Poisson regression in some cases. And because of that, in practice, a lot of times you don't do things like t-tests. ANOVAs you will run into once in a while, but simple t-tests, for example, I've never personally actually had to do in a research project. So unfortunately, at the start, we're going to have to use some simulated data. But when we get to the more complicated stuff, when we get to regressions and such, I'm actually going to use data that I've either published or had in posters and such, so that you can see what these things look like on data sets where it's not canned, where things don't follow the distributions you want them to, and there are outliers. And I'm going to kind of sort of go through the story of how we approach the data in our work to hopefully give you an idea of what we felt like was the right way to do things, and so you can kind of replicate that in your own work or change it if you didn't agree with our decisions. And just a last note, everything in these videos is subject to change. Please give me some slack. I've never really done this kind of a thing before. I've never posted anything to YouTube, to be honest. There's going to be some mistakes because I've never done it before. So, cut me some slack. And thanks for taking the interest and taking the time to watch these videos. I'm crazy excited to make them. And yeah, I hope you enjoy them. Have a good one.